Start with the prayer. Father, Son, Holy Spirit. Hail Mary. Lord is with thee. Blessed art thou amongst women, and blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners, now and at the hour of our death. Amen. Father, Son, Holy Spirit. Amen. Great. Start by just taking a peep at our My Notre Dame page. So setup is going to be the same as last year. So the agenda for the week, the links, this is where we'll put the videos for class. The announcements has my contact info in it, syllabus, some downloads already in it. Make sure you do all the way down because your PDF of your textbook is there. You can take a physical textbook also. We'll sort that out a little later if you want a physical copy also. Happy to do that. Or if it's a situation where it's like, I'm just going to, you can leave, just use them in class, and then you have the digital for home or whatever works. It's fine. If you want one to take home, though, let me know because we have to do some paperwork so I know who has what. Cool? All right. Again, same thing. Everything's on the bulletin board. There's no other places I put anything on My Notre Dame. So should be same as last year, right? Easy. Syllabus. Let's burn through that real quick. So set up for this year, 50% tests, 10% homework quizzes, 25 homework, 15 exam. Notice those percentages changed a little bit from last year as I'm emphasizing a little bit different things. Since this is an AP course, 90 or higher both semesters get you that fancy certificate. For homework, it's a little bit different than last year. So we're still going to have like a weekly problem set that's due Sunday midnights. And that homework is just graded 5 points on completion. The second type, we will have some daily homework this year. Those daily are going to be multiple choice practice AP questions. And that'll be they'll go through the AP Central, and those are going to be graded on correctness. Now, there's still going to be homework questions, so they just get piled in the homework category or whatever, along with the weekly problem sets. We'll see kind of how that's going, but that's my plan there. And we'll show you how to do that here. I have a sample one already set up for you guys to do that's not math related, so nobody panic. All right. Late assignments, I'm going to try to rein these in a little bit because some of us got real far behind at points, and we're going to do a better job of trying to keep up by actually doing some deductions. Now, the first month or so, while we're still getting used to syncing everything and all that jazz, I will waive all of these things for the first month or so, but after that, we've been doing this for 2+ years for some of us, so, we should be getting pretty good at this by now anyways. And the homework sets for this class will be considerably shorter than the trig homework sets. Not that it'll be less time because the problems might be more difficult, but certainly less problems for sure. Homework quizzes, again, same kind of setup. We're going to either have free response style questions that could be done with or without calculator. We'll do those in class with pencil and paper at our desk. Or we might have multiple choice questions that are done without calculator. These guys would be done as multiple choice questions, 1 point right or wrong, run through that myAP site. Again, we're saying the AP exam, everybody has to take it. There's 4 sections. There's a multiple choice section with calculator and without, and a free response section with calculator and without. So we're going to practice doing all of these things throughout the course of the year. The free response stuff won't come till later because the free response stuff always is combining lots of topics. But the multiple choice is very narrow, really looking at one topic, and we can start those immediately. And we'll practice for sure the multiple choice stuff throughout the whole course of the year in both the daily homeworks and on these homework quizzes and stuff. Since probably most of us, was last time you took a multiple choice math test, SAT, ACT, maybe if you took the AP Stat, there's multiple choice in there, but it's a very different skill that really requires a little bit of practice. So we will be doing that on a regular basis to kind of keep ourselves, ready for that. Tests all the same. If you're an extra time person, you got to schedule that through counseling and let me know. Just the only thing I say is that really needs to be done in one setting. You guys are seniors, so the dress code, computers, academic honesty, all that stuff is normal. If you miss a homework quiz, same deal as last year. Come back during commute time. We'll knock that out. If you miss a test, you got to do it in study hall or testing room. All that times I think are the same. Just let me know within a week or so of being sick what your plan is. Doesn't have to be done in a week or so. You just have to be like, a week from next Friday. Okay. In your study hall. Okay, sure. No problem. At the end of the semester, we're going to drop a homework score, a quiz grade, and the test will take a high test score doubling or a retake capped at 85. Same thing we did last year. The plan, semester 1, chapters 2 through 4. Semester 2, chapters 5 through 8, possibly some of 9, 10, 11, depending on how much time is permitted. That's the syllabus. Cool. Questions so far? Anise?
So does that mean we're going to have probably 3 tests this summer? Or...
That would be the plan. We'll see how, if, again, the first time doing this, if things seem like this chapter is gigantic, maybe it makes sense to stop and do this specific topic, a test, and then continue on or whatever. We'll figure that out as we go, though. I haven't taught this. I mean, I taught this course 10 years ago, but it was different textbook 10 years ago. So.
Are you excited?
Yeah. Yeah, I am. And then just like last year, I have the syllabus sign-in sheet. So this will be your first homework assignment. So Sunday at midnight. And we'll turn this in on OneNote just like we did last year, and I'll show you how to do that here in a second. Okay. Speaking of OneNotes, let's get that set up. So I need you guys all to take out your tablet and fire up your Microsoft Teams. Once you do that, make sure you're on the Teams tab here on the far left, and you should see a 6th-hour AP Calculus there. And I'm going to pause while everybody gets their stuff up and running. Tablets booted up and Teams loaded up. I know the Wi-Fi is always pretty crunchy and slow on the first day, as everybody's probably doing the same thing I am doing right now, and it's a lot of data flying down the old Wi-Fi pipeline there. Anybody still getting here? We're still working? Or waiting? I guess waiting is probably more what we're doing. It's not much work. You got to press a couple of buttons and then just wait for the internet to catch up. I don't want to leave anybody behind, but I don't want to sit here and twiddle our thumbs for half an hour. You know what I mean? It's not hard though. We've done this before. Last year, at least for this class, so it's not. That's helpful, and you're seniors and you pay attention, so that also makes things much easier. Does everybody have a 6th-hour AP in their Teams?
Yeah.
Alexis?
I'll also go down to the IT office later. This is a water tablet. It's not letting me sign in.
Okay. That's okay. Doesn't need to be done today, but we're recording all of this, so if you forget the steps, you can always go back and find minute 9 or so of the video and get caught up here. Cool. Jillian, are you figured it out? Cool. All right. So go ahead and pick 6th-hour AP Calculus. Should put you into a screen that looks like this. From this middle navigation pane, pick Class Notebook. That'll eventually load in a OneNote into that right pane. Once all of that stuff comes in and populates, it takes a second. What you're going to be looking for is the Open in Browser dropdown. And you just need to pick instead Open in Desktop App. You can ignore that pop-up and just, there you go. Once you've done that, it's all done. Never need Teams again. At least for what I'm doing. You might need Teams for some other class. I don't need Teams again. Okay, if anybody has problems, holler at me. I'll come by and help you out, or you can ask your neighbor if they got it. But same thing we did last year, right? Which is helpful. Yes, sir.
So let's do like Sunday after that, right?
Correct. Yeah. Same deal as last year. And we all know that like Mr. Kulik doesn't really do anything until Monday morning at the earliest.
Yeah.
So even if it's first thing Monday morning that you're like, oh shoot, I forgot to move this stuff in or whatever, nobody's gonna know. You know what I mean? All right. Everybody got their OneNote up here now that was able to? Oh boy, that was not even really English. All right, same deal as last year. We have collaboration space. We never use that. We have the content library in there already. I have the syllabus and the syllabus sign-in sheet. So we're going to be turning in your sign-in sheet via OneNote. So if you are, I'm going to just do this on my tablet and have my parents sign on my tablet. You can go ahead and copy this into your shared section. Or if you're a paper and pencil person, like that's cool too. If you look in your section, you'll see that I've already loaded 3 tabs in here. There's archived homework for things that have already been graded. Current homework, that's the stuff that I would be grading that week. And then you have a space for notes and handouts if you do notes and stuff in your OneNote. Not everybody does, so. Everybody cool? Okay. All right, next thing, if you guys can take your tablet and go back or go to your the bulletin board for this class on My Notre Dame. We're going to set up our AP Classroom account because this is going to be where we're going to do, we're going to take these multiple choice practice quizzes. It's all going to be through that. So we're just going to register there. So if you go to the bulletin board under links, you'll see myAP. Go ahead and click that. That'll redirect you to the AP site. And I'm already logged in, so it's not doing what it's supposed to, or what I wanted it to. Oops. Try that again. So if I click that now, you should be, well, some of you probably have an AP account already, right? If you have an AP account, go ahead and sign in. If you don't, you'll have an AP account already. You'll do the create account and start filling that stuff in. When you're asked or prompted for a section code or class code or whatever for the AP Calculus, this is the number that you need.
Is it the same thing for both 5th and 6th hour?
No, you have a different code from.
Because that's 5th hour.
Oh.
Yeah, I think I just accidentally.
Oh boy, my apologies. Let me look.
Disappoint. Oh, got out. There you go. You're good.
Let me look here. There's the right one. Let me move this here and fix that real quick then. Thank you, guys. Oh, actually, cancel. I see what happened. Okay. I see what I messed up. That's a bugger. All right.
I don't have student ID. We don't have.
I don't think we have.
I don't think it's a required. If you look at it, I don't think it's a required thing. Am I wrong on that? I don't think it's starred or whatever as required. All right. There we go. Let me put that back up for you guys. I'm sure somebody was still like, I needed that. Which is totally understandable. All right. Once you're through, you should have something that looks similar to this, although I think yours has like My Assignments or something down here. If you go ahead and click that, you should see that I have an assignment set up for you already.
Sample assignment?
Yeah, it's called sample or whatever. Go ahead and do it. It's one question. I'm not worried about right or wrong. It's just as a practice to do something. It's kind of supposed to be a funny math joke. Depending on how nerdy you want to be. Or how nerdy your humor is, at least.
It told me to like put in my phone number. And I like.
Yeah. Yeah. You don't remember your own phone number?
No, I know my own phone number.
Okay. I'm going to hassle you by saying that. Oh, we need a verification.
Yeah.
I see. That's fair. That's fair. Yeah. Totally reasonable request, right? I think we know Mr. Kulik well enough to know that, like, if you're just you have good reasons for doing things, it's like the rules is fine, but you know, like, I need my phone to do this. Okay, that's a good reason to take your phone out. You know what I mean? Yup. Okay. How's the sample assignment?
I'm waiting my score.
Oh, okay. Cool.
0 out of 1.
It's like,
Yeah, I
yeah.
messed up in when I created this, which is part of the reason why I created this. So the only correct answer is picking all 4 of them, which is not what I had meant when I wrote it.
Oh.
I thought that when I selected that as an option, it would be any of them would be counted as correct, rather than needing all of them to be counted as correct. Which, you know, we live and we learn.
wait, sorry, where do I go? They were like asking me a bunch of questions.
That's okay. So you should be at a place where it says like myAP or whatever, or AP Classroom or whatever.
Yeah.
And at the bottom, it should say My Assignments. Like on the left-hand side, there's Blake's going to show you.
So I don't know where you are.
That's okay.
This is my first time doing
Here
all
we
this.
go, my AC. So you should be signed in. Go to mine. You've read this probably.
There's about
Courses and assignments, and then have you joined the AP Calc course? So that you just put in a little silly code.
Okay, thanks guys.
You're welcome.
Did you get a 1 out of 1, Julian?
I got a 0.
That's because I waited to tell everybody what you had to do to get the right answer until everybody had done it.
Oh, I didn't do it yet.
Oh, well, there you go.
Oh.
You will get a 1.
Yeah, no, fair enough.
Everybody's, I'm just going to put in a 1 for everybody because,
That's for me.
well, Mr. Kulik tried to design it so that any answer was correct. And in a way, he found a way to make it so like nobody's answer is going to be correct, which is super cool. I know, right? So as in a quick aside, which one of these was most excited? Assuming excited is a number greater than 1, or a whole number greater than 1?
Probably D.
Or it's probably
D. Yeah. Which is the next most excited?
C.
C. And then B. And the least excited was A. So, cool. I think that does it for our setups, right? We all signed up for the AP or the classroom through AP. We did the OneNote. We got seats figured out. We did the syllabus. Cool. Let's get started then. You guys ready to do some calculusing? All right. As a little aside here, the calculus part of calculus class, not bad. The hard part, the algebra. Because all the stuff that we've learned, all the rules, algebra rules that we've learned before, all matter still. Because most problems, most calculus problems that we're going to deal with have like a hard way and a sneaky easy way. And the sneaky easy way often requires a little bit of rearrangement using algebra to make the calculus part really easy. So the calculus part, again, not the hard part. The sneaky algebra rearranging part is often the hard part. I mean, there are calculus topics that are hard, but for the most part, yes?
Do you have an extra stylus or stylus battery by chance?
I do not. But never fear, because remember, just like last year, all my notes are shared with you on OneNote, and the whole lecture is recorded and going to be available. So even if you're in a place where it's like, sugar, but it'll be okay. But I'm glad that you can participate now. I'm one of the people that, like, I don't remember anything. If I can't write notes, it really helps me remember things. So, all right. So this is AP Calculus, right? Calculus was discovered by... Nope. Newton is the one that gets popular credit. He's actually not the sole creator, though. There is a German fellow, Gottfried Leibniz, that also is credited with the discovery of calculus, or I shouldn't say creation, right? Because is mathematics created or discovered? That's like a philosophy question. I don't want to get into that. At the time, this was actually a rather large controversy. So all of this work was done kind of in the late 1600s, like Enlightenment Europe. So Leibniz is actually the first one to formally publish the work or the foundations for calculus. Newton ends up getting the credit at the time because, well, he's more aggressive, has more political connections, like the royal family in England goes to bat for him, and essentially kind of like professionally destroys Leibniz. It's like not a nice dude, professionally anyways. But in hindsight, they're kind of credited as independently both kind of discovering this mathematics. So those are our two founders. Newton obviously is the more well-known of the two. What's Newton most well-known for? Gravity. His sandwiches. Get out of here. You mean the cookies. Gravity, great. What's the story about Newton and gravity? Yeah, so he's sitting under the tree, and the apple comes down and bops him on the head, right? That's the story or it gets passed down, whether it's apocryphal or actually accurate, I don't know. What does this have to do with gravity, though? Newton is interested in how fast that apple is falling in that instant, right? Now, he knows that he can calculate the average speed of the apple by just taking the distance traveled and dividing it by the time elapsed. And that'll give you the average speed of the apple, right? Now, things that fall, do they fall at the same speed the whole time? No, what happens? They get faster as time elapses, right? Up into a certain point. On Earth, anyways. That point is terminal velocity. If it was in a vacuum, though, it just keeps getting faster forever, right? So this question of like how fast that apple is falling in an instant is kind of like the motivating question for the creation of calculus. Okay, so just kind of keep that in the back of your mind. We'll kind of come back to this idea at several points as we formalize the tools here for our introductory calculus. But that's really what we're kind of doing here. So it's a fun history hour there. You get to draw a little picture of a guy under a tree. Unfortunately, the free response questions are not historical based. Yeah, I know. All right. So the first topic I want to talk about, or that we need to talk about, are tangent lines. And we would have talked about tangent lines back in geometry. Does anybody remember what a tangent line was in geometry? Somebody last hour was able to pull this out when I asked.
I don't know what technical way to describe this one. When you have a curve, it's a line that defines the slope of an instantaneous point on the curve.
Okay, so you are one step ahead, which is okay, because what you said was pretty accurate. In geometry, the tangent line was just a line that intersects a circle exactly once. So there's a pretty crummy looking circle. And we'd say that this is a tangent line here. Everybody's okay with that? Does that ring a bell maybe? I don't know. That's something that's covered for like a day in geometry. So if you're like, I don't really remember that at all, that's okay too. Yeah, that would for sure would come up. Sure. Yeah, that sounds right. ACT loves the circle parts of geometry for whatever reason. I think it's because a lot of that gets covered in conics. If you do conics as a pre-calculus topic also. Not everybody does. Okay. We want to, though, generalize this and talk about tangent lines not of a circle, but we want to talk about tangent lines for a curve. Or a function, let's say. Okay. Oops, I thought I changed my color. Okay. So let's say we have some curve with some point P on it. The tangent line for that curve would be something that looks like this. Notice, does this tangent line have to intersect the curve exactly once? No, like clearly this one doesn't. It could intersect it more than once. But what we should be able to say is that there's some region or some neighborhood surrounding P in which the tangent line does intersect exactly once. Everybody's cool with that kind of fuzzy definition of just like some neighborhood? Basically, you should be able to zoom in enough to where it's like, yeah, there it is once. Cool? All right. So, if I want to describe that tangent line, what do I need to describe a line? And a point? Okay. Do I have both? Don't know the slope, but I do know the point. I know it's going through P, right? So what I need is what? We need that slope of the tangent line. Now to calculate a slope, what do I need? 2 points, right? Do I have 2 points on the tangent line?
Yeah. Yeah, outside of the neighborhood.
You know those points?
No.
No, right? We've just kind of drawn it in there, right? The only point we know about is P. We know it has to pass through P. All we know about is the function. We don't know where that tangent line really is going. So what can we do?
Can't we use like the point P and then use the information from like the actual curve, like
The function.
function, sorry.
That's okay.
Then you can use that to find slope.
Okay. So what I think Blake's saying is that the slope of the tangent line is going to equal the slope of the function at P. Now, a couple of things that may be setting off some alarm bells there with that statement. One of them is, do we have slope for non-lines? Like our function is not a line, it's a curve. So that not really called slope there. But we could just say the rate of change between 2 points. That would still be accurate. Same thing as slope still. But how many points do we need to calculate a slope? 2. What do I have here? 1. So what am I going to do? Well, I'll just pick some other point on our function. Maybe I'll call that point Q. And look at the slope of PQ as Q is getting closer and closer and closer to P. And use that to approximate the slope for P, or the slope at P. Right, so let's do this with a specific example. Sound good? Oh boy. So let's say we have our function here is just our good old f of x equals x squared. Let's say this is our point P at the point 1, 1. And we'll start with some point over here, Q, where Q is going to go and get closer and closer, right? So maybe we start with 2, 4, and then we go down to like 1.5, comma 2.25, and then maybe 1.25, comma 1.5625. Just as an aside, how am I getting these numbers? All I'm doing is I'm taking the x coordinate and plugging it in to the y for my function to get the y coordinate, right? 2 squared is 4, 1.5 squared is 2.25, et cetera, et cetera, et cetera. Is that still okay with everybody? Okay. So then we'll just calculate that slope for the line PQ. So if I use that first value for P, I get, or first value for Q, excuse me, I get 3. If I use the second value, I get 2.5. If I use the third value, slope, right? M is the symbol that we use to abbreviate a slope. Slope of PQ.
Yes.
That simplifies down to 2.25. I'm not doing these in my head. I've just done them in advance already for you guys. So what does it appear that this slope of P is approaching? As PQ, as those points P and Q get closer and closer together, what does that slope look like it's approaching? 2, right? Everybody seem like that's a reasonable guess? We went from 3 when it was far away, we got a little closer, went 2.5, got a little closer, it was 2.25, got a little bit closer, it's 2.1. Seems like it's probably heading to 2, because we're pretty darn close at that point, right? We're 0.1, away on the x, which is pretty close. What did we just do? What is this process? This is something we did last year. Anybody remember what this process was called? That's okay. This was a limit. So what did we really do? This was the limit as Q approaches P of the slope of PQ. Now this is something that's geometric, right? P and Q are points. PQ is, or MPQ is a slope. Let's algebra this up. So really what we want is the limit as the x-coordinate is approaching the x-coordinate for P, which would be 1. And then the slope, well, the slope of the function would be, or I'm sorry, the y-coordinate of the function is going to be x squared, right? Because our function is f of x equals x squared. The y-coordinate from P is 1. The x-coordinate of our function, well, that's just going to be x because you plug in whatever. And then the x-coordinate for P was 1. So this is like qy. Oops. This is like py. This would be like qx. And this would be like px. Oops. And then this guy would be like px. And this would be like qx. Right? As the x-coordinate of P, or if Q gets closer to the x-coordinate of P, the slope then is this, right? We just did slope formula. Is that okay with how I kind of constructed that?
You lost me when you started labeling like qy.
So qy is just the y-coordinate for the point Q. And py would be like the y-coordinate for the point P.
And so then you got that because if you plug in 1 in the function, you would get x squared as your y.
So like P is just the point 1, 1, right? That was defined. Q is not defined to be a specific point anymore. It's x comma f of x,
Okay.
right? And f of x is x squared.
Okay.
Cool?
Yeah.
Perfect. Yeah, anytime it's not clear, feel free to ask and we'll clarify. Jillian.
So how would you say the limit of the Q arrow, how would you say that like out loud? Like,
Oh, the first part?
Yeah.
Yeah, that's the limit as Q approaches P of the slope of PQ.
Okay.
Blake.
But then how did you get x squared for like qy?
So if I look at the point Q, if I don't give Q a specific value, it's just a point on the function.
It's just then it's just x squared.
It's x comma f of x, which is f of x was x squared, right? Any point on a function could be defined as x comma f of x. And our f of x in this case was specifically x squared. Does that feel okay? So what we've done here is we took a geometric idea, right, taking the limit of the slope of 2 points as the points get closer together, and expressed it algebraically, right? Now the green circle looks like something we would have done last year. Everybody agree? When we did something like that last year, how did we do that? Do you remember? We usually use the table, right? So we pick some values that were bigger than 1, but getting closer. So like maybe 2, 1.5, 1.1, 1.01, getting closer down to 1. And then we pick some values that were less than 1, but getting closer. So maybe 0, 0.5, 0.9, and 0.99. And then we evaluated them using our calculator, and we're really looking at those two to see kind of what we're getting close to, right? So let's just run through using our calculator to do that. So I do alpha y equals. I'm in the y equals menu, and I did alpha y equals, and I'm just going to type in the function that I'm taking the limit of right there. Feel okay? And then what I think the easiest thing to do then is to exit out to the main screen. I'm going to retrieve the y1 variable by pressing the vars button, going over to yvars, and from function selecting y1. And then I'm just going to do y1 of these values. So I got 3. We did that up above, 1.5. We did that up above, 1.1. Things are getting smaller still. And then the last one I'll do in the above direction is 1.01. Very close to 2. Now if we go from the other direction, if we come from below, we started with 0, and then we did 0.5. So I see we're getting bigger this time. And we did 0.9. Still getting bigger, and then 0.99. And what we have here, if we compare them, indicates to us pretty closely, or pretty strongly, that's going to be 2, right?
How did you get to the bars again?
Vars is a button below the down arrow. And then you went over to yvars, and then function, and then what you needed. Okay. Alternatively, what's the other way that we could have done this, other than making a table like we did, which is perfectly valid at this point in our education to make a table to evaluate a limit. The other way would be to look at the graph. So if I look at the graph of this, if I look at where x equals 1, it appears that the y coordinate there is 2. Now if I try to actually evaluate that by doing the value, notice what am I getting? Undefined, right? Because if I actually plugged 1 into here, what would I get? 0 over 0. Okay. So if I zoom in enough, you'd see that there's like a gap in that straight line where x is 1. It's a removable discontinuity was the technical term we used last year for what was going on there, where there's just a little hole in our graph like that. So once we've ascertained that the slope is 2, I can now write the equation for my tangent line. So remember, I like to use the point slope equation for a line. Oops. So our x1 and y1 here is the points for P, and our slope would have been the 2 that we just found. And when I simplify that down, I get 2x minus 1. So that should be the equation for my tangent line. Just for the record, instead of using the point slope equation, you could use slope intercept. You could just use y equals mx plus b. The disadvantage with that is you have to solve for b, which is not that big of a hassle, but I like doing this because I can just rearrange it and not have to like solve for b and then plug it back in. When I'm done, I'm just have my equation. And do I expect you to remember that? No, but the AP would. Here's the downside. You know what the equation sheet looks like for the AP exam? It's a blank piece of paper.
Nice.
So,
Hope they really know how to treat us well.
well, I think that they would give you things that are kind of obscure, but something like the equation for a line, they'd expect you to have that memorized.
Are we getting these equations on our tests?
I would say that I would give you equivalently as much as the AP would, but I will tell you in advance. Maybe we'll make a running thing in OneNote of like equations to make sure that we have memorized.
Okay.
That seems like a reasonable thing to kind of collect together.
What about that circle?
The unit circle?
Unit circle.
Yeah.
Okay. Sounds good.
They expect you to be able to evaluate unit circle values.
So they at least give us like a circle.
Nope.
Okay, so we can draw ourselves off the board and take it to most.
We can talk about this as things get a little bit closer about the way that I do this, because I don't memorize a unit circle. I just draw 30, 60, 90, and 45, 45, 90 triangles
Numbers, yeah.
and put the numbers in there, and it's
Yeah, I'm not memorizing.
Yeah.
It's like, wait,
yeah, it's a lot. So I'm going to memorize these two triangles that I already know, and then just draw a picture. Anyways, we're getting off track. Okay. So we have this idea of we can find the slope for a tangent line by evaluating a limit that'll give us the slope at a point, right? Which was what Jillian had said before when we asked about a tangent line, right? It's the tangent line slope was the same as the instantaneous slope of a function, right? The slope at a point. So this, at least for our starting point, the key mathematical tool that we're going to be using is the limit, right? What's the definition of a limit? It's good that nobody's answering because we never gave you a formal definition of this. Let's do that now. So this is now section 2.2. And before I get too deep into this, just to let you know, this is not something that you would need to have memorized or even something that we're going to work with explicitly. I'm just going to use it to kind of build some intuition for you guys because it is beyond the scope of this class. But I'll frame a little bit of why the definition is what it is and why you might care about it. So this is often referred to as the epsilon delta definition of a limit, since those are the two.
What's that symbol? After for every number.
So
greater than 0.
this is epsilon, and this one is delta. They're both the lowercase versions of those Greek letters. So the uppercase delta is the triangle that maybe you're familiar with from physics or chemistry or something else. I think both those classes abuse that capital delta to do things. Delta K, I think, is a chemistry thing, or delta Q, right? When you're doing KSPs and stuff. I don't know. Do you do that in all the chemistries? Yeah, I think that's all stuff that when you do thermodynamics and kinetics that comes up. Anyways, this is often called the epsilon delta definition of a limit. Before, what we did when we built a table to evaluate the limit or looked at the graph to evaluate the limit, all we're doing is taking a guess. Now, at this level, that guess is probably going to be right. But to prove that, for example, in that last problem, the limit was 2, we would need to go through and use the definition to show here's an epsilon and a delta, and then it always is going to be, satisfy these 2 bounds. Let's talk about intuitively what this is really telling us, because that's the part that really is, that matters. So say we have, oops, that curved a little bit wonky on me. Say we have some function here, and here's our value for a. So this spot, let's say, is a plus delta, and this spot would be like a minus delta. Everybody's okay with that? So this point here would be the limit as x approaches a. So that would have the value L. And then this point over here, let's put some dashes in for us. This would be like L minus epsilon, and this spot up here would be like L plus epsilon. And what we're really saying is that if we look at that distance, the distance from A to delta, as that distance is getting smaller, the distance here from between L and epsilon is also getting smaller. That is, if we squeeze down on that value for x, it's going to squeeze down equally on a value for y, or equivalently to a value of y. So as we approach x, it's going to approach a y, the limit. Does that feel okay? And again, this super technical definition that we've just spelled out is something you'd never need to use in class. Okay? But this is how you would prove that a limit is actually the number it is. Or one way you could prove. We'll do some proving limits have certain values with theorems that don't involve the definition. But there's things that you have to use the definition to do. And those are things that you might do in like a Calc 2 or 3 course. Some of us that are planning on being engineers will probably have to do that at some point in a Calc 2 or Calc 3 class. So I think most engineering programs are going to require up through at least Calc 3, and then either a differential equations course or call it just Calc 4. I don't know. Depends on your university. Okay. So let's go and just practice evaluating some limits. Okay? So I'm just going to write down some limits, use the table or graph method that we've talked about to evaluate the limit. So take out your calculator, follow along. We'll give you some time to play around with these and we'll talk through it. Yeah, no problem, dude. Got one powered up just for you. Yeah, of course. Sure. No problem. Anybody else while I'm digging out calculators?
Thank you.
No problem. So the first one, the limit as x approaches 1 of x minus 1 over x squared minus 1. Can anybody do this without the calculator? Based on the previous example, you should. What was the previous limit we just did? Okay, it was the limit as x approaches 1 of x squared minus 1 over x minus 1, which was equal to 2. This one is the limit of x minus 1 over x squared minus 1. The two functions we're evaluating the limit of were reciprocals, so you'd expect the limit to be 1/2, the reciprocal. And that is indeed what it is. That's okay. To confirm that, let's just kind of look at the calculator. Notice that the graph that I'm going to get is going to be very different than the previous one. The previous graph was just a straight line. This one is going to look like a rational or simple rational function.
Wait, how do you get the L? How do you do the fraction?
Oh, alpha y equals. Yeah, no problem. And I'm just going to shrink this viewing window down to be something that's a little bit more appropriate. So again, if I look at x equals 1 and I trace that over, that looks to be about 1/2, right? Everybody agree? Or you could build a table and evaluate. Oftentimes it's best to do both. We'll see an example where the table is misleading. Whoa.
Can you explain that again?
Sure. So when I'm looking at the graph, the limit that I'm worried about is as x approaches 1.
Yeah.
So I'm using 1 as my x coordinate. I'm tracing up to the function to find the point on the function where x is 1, and then tracing over to the y-axis. And that looks like 1 would be up there where the graph is crossing, and 0 is down there, so it looks like it's in the middle. It's probably 1/2. Or I would evaluate and I notice that there it is again, indicative of 1/2 when I get pretty close on either side.
How do you do like tests, like you type an x value on your graph?
So you press second and then the trace button and select the value command. The problem is if I press 1, there's nothing there because when I plug 1 in for x, I have 0 over 0.
Sorry, what was the in the graph? You know how there's the like that little circle that means like there's nothing there. What is that called?
Removable discontinuity? Yeah, no problem. These are all great questions. Let's try another. This one I won't spoil. I figured I would spoil this one though before everybody did a bunch of work.
Can you explain how you do that one conceptually so fast?
Yes. So the previous problem that we did, we did the limit as x approaches 1. So we did this in the previous example, Jillian. And I noticed that those two parts were reciprocals. So I figured the limit then would be the reciprocal.
Oh, okay.
And that is indeed what we saw when we looked at the graph and did a table. This next one, doing the fraction command when you look at the graph, is enormously helpful in getting this typed in correctly. If you haven't been doing that, that is a good one to remember. So I've gone ahead and graphed this. That's usually my first step because it doesn't require a lot of work. And at x equals 0, this looks like, I don't know, 0.1, 0.2, 0.3, something like that. I'm not really sure, so I'm going to go build out a table. So I'm approaching 0 this time, so let's do 0.01 and then negative 0.01. Anybody recognize that as pretty close to a commonly occurring fraction? Yeah, that's pretty close to 1/6. That is indeed what this is 1/6. If you had wrote it as, you know, that's also okay.
Could you do the plugging in with your Y-bar?
Oh, to get the y-var?
Well, so I've got,
So you press vars
and then,
over to y-vars,
okay,
and then pick function,
yeah.
and then there's the y1. The trick is, though, after you've done that once, if you press second and enter, you recall the last thing you had, and you can just go back and edit it.
And you're, okay, so we're approaching the 0, so you're,
That's why I've changed the values. Yes, I do a little bit above and a little bit below,
okay.
or very close above and very close below the value the limit is approaching. Yes.
So is it best to first graph it out and then see where you're kind of going to be at and then base your points on
The graph, to me, the graph is typically more valuable than the table. I'm going to go to the table if I look at a problem like this and go, that doesn't look like a whole number. Let's try to figure out what that specific value is. But if it looks like it's just a whole number, I'm probably just not even going to bother with the table.
And then, so you want points pretty much as close to 0 as possible.
Correct, as close to whatever the limit is approaching. In this case, since the limit is approaching 0, I want them pretty close to 0. Usually to the 100th is fine. 1,000th is better. You know, you don't want to make them too big because sometimes the calculator gets funny about rounding and it'll do something strange on you. But usually 100th or 1,000th is plenty to get a good picture. Does that feel okay so far? Okay, let's do some more. We're going to do a bunch of these because this skill that we're practicing right now is going to be super valuable for quite some time. So the limit as x approaches 0 of sine x over x. Since we're about to graph a trig function, what do we have to be careful about? The mode on your calculator. What mode should you be in to graph a trig function? Radian mode. So if you tried graphing this and not much happened, your mode would be the problem. And just as an aside, why can't I just reduce those x's? One is inside the sign and one is outside the sign, right?
Isn't sine limited to 1?
Sine is bound. The values of sine are bounded between -1 and +1, but you're also dividing by a variable,
Okay.
right? So if the x is like 0.1, it now be between -10 and +10. Or if the x is 0.001, it's between -1,000 and positive. It's not very like that is true. Not very helpful in this case. But remembering that would be helpful much later when we talk about some other limit rules. There's an important limit theorem later where remembering the bounds for your trig function can be very helpful. So I'll start by looking at the graph. What's the limit? Looks like 1 to me. Right? So this is 0. That's 2. You just can't see the tick mark because,
So for these, you want us to like typically round up because when I plugged in 0.01,
Mhm.
like the parse thing, it was just like 0.9999.
Yeah. So again, all you're getting from this is like an approximation. You're going to use some common sense there. But yeah, I get the same thing. And if you wanted to be sure, you can add like another 0 in front. Can be 0.001, and you'll get even more 9s. At that point, you should be pretty convinced that it's just going to 1. You okay, Blake?
Good. Yeah,
Okay.
sorry.
You're making faces. I'm just
Yeah.
checking. All right. Next one. So if we look at the graph of this, that doesn't look very helpful to me, right? Looks like at x equals 0, we have something up here at like 1 and something down here at -1. Maybe I just need to zoom in more, right? That's some pretty erratic behavior going in there. Maybe it'll settle down if I zoom in more. Maybe I'll go from -1 to +1 on the x. Maybe that'll solve it. Okay, well, maybe we just need to zoom in some more, right? I can keep zooming in. Maybe we'll go from -0.1 to +0.1. Maybe that'll solve it.
I don't think it worked.
Something wrong.
Yeah. That's interesting. Well, let's go look at the table then. Right? Okay, I got 0. And then, oops, I got 0. Oh, so the limit's 0, right? That doesn't seem to be backed up by the graph, right? So what's going on here?
Is it like everywhere?
So the answer, the way you'd want to answer something like this is does not exist. So you Mean Girl fans in the audience, yeah, the limit does not exist. That's a normal phrasing. That can happen. Why are we getting the zeros here when we do this? Like this strongly would suggest to you, if you're doing just the table, that the limit would be 0, right? Even if you picked 0.001 and -0.001, you're still going to get 0. You can get 0 for as many zeros in a 1 as you get. Why do we just keep getting 0 here? So remind me again, when is a sine function equal to 0? What values of x make sine 0? Just on the unit circle would be fine.
It would be pi over 2 and pi over 2.
That's cosine.
Oh, dang it.
Pi
And 0.
and 0 and 2 pi.
Yeah.
In fact, all multiples of pi make sine 0. So what does 0.01 or pi over 0.01 simplify to? Pi over 0.01. 100 pi?
Yeah.
0.01 is
yeah.
1 out of 100.
True.
So that simplifies down to 100 pi. That's why we're getting a 0 there. So for this problem, if I used any decimal that was equivalent to 1 over some fraction, or 1 over some, is a frac. If I use any decimal that's equivalent to the fraction 1 over something, it's going to give me a 0. Now, if instead I had used maybe like 2/7, right? That's not equivalent to 1 over something. So I get something different. And then I could make maybe like 2/11. That's getting closer to 0. That's not helpful. 2/15. Maybe I'll try. Is that gonna? Yeah, it's still giving me problems. So like this one is problem all the way around, right? Yuckarooskies. So this one, looking at the graph, almost, if you tried to do a table, almost no way you're going to get that correct, right? Looking at the graph and seeing all this erratic behavior is what you needed. Everybody okay? And this is a pretty canonical example. Sine of 1 over x is a limit that does not exist that will pop up rather frequently. I've seen it on many of the AP exams in one form or another, which is all this really is, right? It's just the constant at the top is pi instead of 1. But that's a limit that'll pop up rather frequently. We got this good stopping point. That sounds good. Let's stop here. We have 2 minutes left. So